Okay, so welcome to the Harvard Bioinformatics Coffee Hour. Today we're going to be doing some very basic introduction to Ggplot. And like we've done for previous ones of these workshops, we'll be using the My Binder setup to run our studio. So if you haven't already, go to the Harvard Informatics GitHub page, scroll down to Ggplot Basics, click on Launch Binder, and you should get an RStudio window that looks kind of like this, and we'll be working from this index.rmd markdown file. Now I have this all in markdown format. If you want to knit this and then save it away somewhere, you can have the nice HTML with all the inline plots and everything. You can, of course, just go to run and run all the chunks, and you'll get everything. In the interests of sort of walking through the code, I will probably not do that and instead run things from the script in the console. But you can also just hit play on these blocks to run blocks, right? So that's going to run that block, and what we're going to be doing today is looking at Ggplot and sort of talking a little bit about the basic way to use Ggplot to make both simple exploratory graphics, and although we won't really get into it much today, complex publication-ready figures. And to do this, we'll be using Tidyverse, obviously, but also this R package DS Labs that includes a bunch of already cleaned and tidied and nicely formatted data sets for doing these kinds of workshops. So these are a variety of different data sets. And the main advantage of these is that most data sets you can find from your own science or just from the web start out fairly messy. And as we went through in the past few weeks, the material that Brian Arnold covered last week and the week before, there's a lot of work that goes into tidying up this data, manipulating it, making it clean and easy to use. And rather than include that in today, just for time purposes, we're going to start with stuff that is nice and clean. So let's load this DS Labs package as well. Okay, so a really basic introduction to Ggplot. It's often called, the grammar of graphics. And conceptually, Ggplot is quite different from base R plot functions because the way it works is that it builds up graphs in a consistent way. So there's three things that make up any plot in Ggplot. There's data, obviously. You can't make a plot without data. There's aesthetic mappings, which basically set up things like your coordinate system, the scale of your axes, properties like this, what groups are going to be plotted with which color. And they're basically saying which variables in your data map to which visual properties. So what variable maps to the x-axis, what variable maps to the y-axis. But this doesn't actually make a plot. This just sets up a plotting area, basically. And then you can layer on top of that one or more of these geometric object functions, Genomes, which tell Ggplot how to render each observation. So how are we going to translate this data into these aesthetic mappings? Because there can often be many ways to do that. So the basic command, which we'll use a lot here, is Ggplot data, some data set, AES, which stands for aesthetics, and this will then have the mappings. And then we use a plus sign, and then we have some geom function and possibly some options. So let's start with something really basic. So this is a fun data set that's included in the DS Labs package, which is from the website Spurious Correlations, which is worth poking around if you haven't ever seen it. It's It's just pulling random variables from two large data sets and identifying ones that have very high correlations, but of course have no relationship to each other. So what we're going to look at here is a data set that has the divorce rate in Maine and the consumption of margarine, which are highly correlated between 2000 and 2010. Okay, so we'll load this data, and I'll keep the console open so the commands will go down here. And let's just make a basic plot, right? So this is going to use this divorce margarine data set. Our aesthetic mapping is going to set the x-axis to be equal to the divorce rate in Maine, and the y-axis to be equal to the margarine consumption per capita. And then we'll use the genome point, which is just going to do what it says, make a point for each one of these data sets. Or make a point on our aesthetic mapping for each row of the data frame. So here's the plot. Let's see if I can make my window a little bit bigger here. So you can see this is pretty simple. This looks somewhat similar to what the similar plot would be in base R, which would be just the plot command with x equals divorce margarine $, divorce rate Maine, and y equals margarine consumption per capita. And this is very straightforward. These things are, each one of these points represents a different year. These things are highly correlated. When people eat more margarine, people in Maine are more likely to get divorced. So let's break down this plot a little bit to try and get an intuitive understanding of how this works. So the first thing we'll do is let's see what happens if we just run this AES command. We don't do any genomes at all, right? So if we run that, we get exactly the same XY axis, right? We get the same plotting area with the same labels, the same color scheme, the same tick marks and everything, but of course no data is plotted. So this, if we scroll up here, these two look exactly the same. So this is what the AES statement is doing, is just making this area. And then any geom we stick on top of that then adds a layer on top of that that includes points. Now we can add multiple layers, right? So it doesn't have to be just one layer. And we can also say assign this plotting area to an object, right? So let's do this. We're going to assign this this plotting area that we've created to the SpurCore object. And now if we want to try different ways of different geomes, different ways of mapping the data to this aesthetic, we can just run those without having to recall this Ggplot statement, right? So we're going to use the SpurCore object, which is the data and the aesthetic, and we're going to add geom point. So this is just what we did before. Then we can add geom point, and we can add geom smooth, which is just a line, right? So now we have both of these on top of each other. We have the points and the lines. So as long as the aesthetic is not changing, you can just keep adding as many different geoms as you want on top of this, right? So we could, I'm not sure what other way it would make sense to plot these data, since it's a very simple XY scatter plot. But if you wanted to do something like add another, here, let's just modify this, right? So the default way to do a geom smooth is using a low S fit. So we'll do the default, but then let's also add another geom smooth, another line that has a few options. So we'll say method equals LM, and we'll say color equals red. And now when we run this, we get two lines on top of each other, one showing the low S fit and one showing the linear model fit, right? So you can just arbitrarily just stack these layers on top of each other however you want, and they'll just layer up from top to bottom. Now, in this case, is that useful? I mean, we could just keep putting every possible line on here that we wanted, and it wouldn't necessarily be that interesting. But I think the goal here is to sort of give you a sense of kind of how to build up these plots and how it's becomes easy to just add things on top of them. So for example, one of the challenges in base R is that doing this kind of thing, adding a fit, is not always straightforward, and certainly adding 3 different fits to the same plot can get quite complicated, whereas here it's just a simple matter of layering. Okay, so here's that plot again. I just by itself now without the points, right? So here we have the LM. The default formula is always y equals x, but you can specify a different formula if you want. Right, so now you can see, of course, in this case, because we just used the geom smooth, again, the aesthetic stays the same, but we don't have any points, right? We didn't include the geom point. So again, the spur core object itself just contains the coordinates. And then we can add whatever geom mappings we want on top of that. Okay, so the basic framework, data, aesthetic mappings, geom. As an aside, there's a huge number of options in Ggplot for controlling the way that these plots look. So this is the default. And you can modify these aesthetics, especially things like, you know, we'll talk later about modifying the X and the scale of the axes, but say the color of the background, the tick plots, the sort of basic way that the graph is set up. You can modify all of these. And one kind of simple way to do that, which we'll get to later, is with themes, but there's also lots of more complicated ways to do that. You can create your own themes so you can have a consistent look for all the graphics you make. We're not going to get into the sort of detailed, complex ways you can modify those aesthetics today. I'll show you a few themes later. But there's a couple of links I put here that have other tutorials on the internet that have more detail about, you know, kind of at least some tips and tricks for how to modify these sorts of things. Okay, so let's get a little bit more complicated now, and we're going to use a different data set that has more variables and more complexity to it, called the Gapminder data set, which I meant to look up. I'm actually not sure why it's called Gapminder. It's a data set of life expectancy, GDP, infant mortality, a handful of other things for, you know, from 1960 to 2010 or so for most countries in the world. So we'll load that data. If we want to, we might want to do something like, you know, head Gapminder just to see what this data set looks like. And so you can see we have country, year, infant mortality, life expectancy, fertility, population, GDP, continent, region. So it's essentially a small number of variables for a large number of countries. Okay, so we might want to make a really simple plot, right? Like life expectancy versus per capita GDP. We notice that per capita GDP is not in here. Of course, one thing we could do is use the mutate statement to add per capita GDP, but we can also just define variables in this AE estimate. Oftentimes, this is probably not the best way to do it. If you're, you know, actually making a graph for publication, you should probably set up your variables and check them for errors and things like that. But for simple data exploration, this can be really useful. So here, for example, we're making the y-axis to be GDP divided by population, and Ggplot will just make that data transformation for you. So we run this, and we can see our x-axis is life expectancy, our y-axis is GDP divided by population, right? You know, we could do other things like log transform this. You know, you can do other data transformations in these axis statements if you want. We'll by default remove missing values. It might be better to have a, you know, a mutate and a filter statement to clean this up ourselves. But again, for sort of exploratory purposes, this is quite nice. So again, this, you know, another thing to note is this default plotting scheme for this maybe isn't so informative. Like tons of plots are stacked on top of each other. this is plotting all countries and all years right on top of each other, things like that. So we might want to do, a few other customization options. And so one thing we can do that's very common is, we want the points to be colored by some sort of group. So this is also something you can add to your AES statement. So here we'll filter to just be 1 year. We'll remove missing data. We'll make GDP per capita as with a mutate statement. And then we'll pipe these modifications into Ggplot. So we'll use life expectancy and then the variable created in this mutate statement for the Y value. And then we're going to add this color equals continent to our aesthetic. And so here's what that does. Excuse me. So now Ggplot has done a bunch of things automatically for us. It's grouped the data by continent. It's colored all of the data that comes from the same continent with the same color. And it's made a legend for us that shows us the colors. And again, there's lots of ways you can change all these defaults. You can change the color scheme. You can change the position of the legend. You can customize essentially every visual aspect of this plot. But in order to get through the sort of basic material for today, we're not going to skip that. Andreas, I just saw your question. No, the DS Labs package does not create tibbles by default. It creates data frames. So if you want to make these into a tibble, you'd have to use like as tibble or something like that to transform them once they're imported. Okay, so let's look at a few different a few more sort of customization options here. So a couple of things here. One is, okay, so here we put the color statement in the aesthetic. And what this does is it by default groups, if color is a discrete categorical variable, yeah, well, tidyverse, Ggplot, sorry, answering another question, all tidyverse will work in Ggplot. Ggplot is, I guess, part of tidyverse. So normally when we load tidyverse, we load, rather than loading individual packages, we would load the tidyverse set of packages. If you just loaded Ggplot and didn't load any other component of tidyverse, then you would not have access to filter and mutate and those verbs like that. But so we're using both Ggplot, which is technically just this bit, and dplyr and the other bits of tidyverse, which is this bit. Does that make sense? Okay, so going back to this color statement and grouping. So, of course, we might want to just change the color of the without grouping them all. And to do that, one thing we can do is we can override the default aesthetic, which is specified in this Ggplot command, with another aesthetic in each individual geom. So if we wanted, say, for example, all the points to be red, then we can have this default aesthetic, and then we can add a geom point with the color equals red. And what they do is then make a plot where all the points are red, and whatever we put in the color, whether we put color in this original AES statement or not, it'll get overridden by this additional AES. And we'll see other ways that you can modify the AES for individual layers later in the tutorial. And this can be useful if you want to say, have your plots colored by one grouping variable, your points colored by one grouping variable, and your lines colored by another grouping variable, for example. Another nice feature of Ggplot is that if the grouping variable is not a categorical discrete variable, but a continuous variable, it won't try and make categories, but it will plot this as a as like a scale bar, right? So in this case, where we have, now we're plotting year on the x-axis, still life expectancy on the y-axis, and we're grouping by GDP per capita using the color statement in the AES command here. And this will create essentially a scale bar, right? That's gonna show, that's a gradient of colors. So each point will be colored by its GDP per capita value according to this gradient. And again, as I will keep saying, all of these defaults are modifiable. The color schemes in particular, there's very complex sets of tools associated with Ggplot for modifying these color schemes. But again, that's beyond what we have time to cover today. Okay, so let's see how we can sort of combine these together to do more complex things. So now let's say we want to make all of our points black, but have lines colored by continent. So we'll essentially have a background of points, and then we'll just have a line for each continent that represents the relationship between life expectancy and GDP for that continent. So we're going to add a few things here. We're going to keep this first little bit. So we're just looking at the year 2000 and we're creating this GDP per capita. We're going to log transform the GDP per capita to make this a bit more linear. And in the AES statement, we're going to set color equal to continent. So this will, by default, group the variables by continent and assign a different color to each continent. However, when we get to this geom point, we're then going to override that color statement with color equal to black. And we're also going to set alpha, which is the transparency, to 0.2. So that means each point is mostly transparent. And so when there's only one point in an area, it tends to fade away. And when there's a cluster of points that are overlapping, they tend to stand out. And then we're going to add a second geom, a line fit, but we're not going to override the default color statement, grouping statement here, which means that these lines now are going to be per continent instead of just one line for the whole data set. Okay, so we run that, and here's what you get. So again, you can see the points now are not colored by continent, they are just all black, but our lines are in fact grouped by continent. So again, for this particular data set, whether this is useful or not, I don't really know. I mean, probably you would prefer to keep the points colored by continent. But the general approach of being able to modify the aesthetics piecewise in each geom as you layer them up can be quite useful for creating complex graphs that summarize data in multiple different ways. So I mentioned earlier that there's lots of customization options, and we're not going to get into them a lot. But one thing I do want to show you before we go on to other types of plots is themes. So there's lots of themes that you can find both included in the Ggplot package, in the GG themes package, and in other packages that people have produced on the internet. And these are designed to essentially change this kind of default visual aesthetic of how plots look and make it into something different. So the ones that are with the default Ggplot tend to be pretty simple. If you look in like the GG themes package, there's one that's like the 538 theme. There's one that's the economist theme. I think I've seen an XKCD theme. There's a lot of flexibility with these themes, and it means you can maintain a consistent look across all your plots without having to write a lot of code yourself. And the easiest way to see how these look is to, again, take our full plot statement. So we're going to make a few changes here, which I'll explain in a minute, but we're going to assign this to an object. And now we can just try different themes and see how each theme looks by running this object, which includes all of the plotting information, plus a theme. Okay, so a few more modifications I'm introducing here. We're still going to start with the StatMinder dataset, filter it to 1 year, mutate to create our GDP per capita. In this case, rather than putting log 10 in the y-axis, so transforming the data, we're actually going to scale the y-axis itself. So Ggplot has a number of these functions, these sort of aesthetic changes for modifying, say, how axes work, right? And this scale y log 10 just takes the y-axis and scales it so that it's log 10, right? So the difference being that, say, in this plot, we are plotting log 10 GDP per capita, so we get 2, 3, 4. And what you'll see in this plot is that we get the actual raw numbers. It's just a log scale axis. And there's a number of these scaling functions, and this can also be used not just to transform the axes by log transformation or something like that, but also to zoom into a particular part of the plot, say to change the x and the y limits, things like this. So this is sort of getting a little bit more into the nitty-gritty of how to customize these things by using additional functions like this that can sort of modify the default aesthetic in a way that's slightly different from what we talked about, like using color. Okay, so we just run this, and now we just have this object, and we can apply different themes to it and see how they look. So here's the theme dark, right? That turns the background black. In this case, it's probably not so nice with black points, but if we change the color of these points to white, this might look interesting. The theme classic is a theme that is sort of replicating a very sort of traditional, straightforward look of graphs. You know, very clean lines, relatively few ticks, none of the sort of plot background or anything like that. And then theme minimal is even more reduced, no axis labels, no axis bars itself, just a simple grid and the ticks. And there's lots of these, in particular, the GG themes package contains a bunch of interesting ones. I tend to like theme classic for a lot of things, and theme minimal as well. But there's something like 10 different themes within Ggplot itself, and then, many more in other packages that are available. So, of course, you can create your own theme, right? All of these theme statements are essentially just applying different transformations to the aesthetic. But that requires, that can be worth doing if you have something particular in mind. But of course, that is a lot more work. And if you like the look of theme classic, then you can just use it. Okay, so moving on to just kind of expanding the genomes, right? So we've talked a lot about how to find the aesthetic, how to layer things, the sort of basic structure of Ggplot. But of course, you often want to plot many different kinds of data that aren't just XY scatter plots, right? So, geom line and geom smooth are two sort of common functions for dealing with XY scatter plot data. But there's lots of other kind of data. So one example is, say, one-dimensional plots. The simplest kind of one-dimensional plots are just summarizing the distribution of a continuous variable. So something like a histogram or a density plot. And there's a number of different ways to do this in Ggplot with different geoms. I tend to like histograms and density, kernel densities, but there's also a frequency polygon, and I'll show you a bunch of them. There's a few things to keep in mind here. So, of course, in this case, we only have one variable, right? Life expectancy. In this case, we're going to look at a histogram of life expectancy. And so we're not specifying both an X and a Y variable for aesthetic. Now, there are some additional reasons why you might want to specify both an X and a Y. And in fact, if you, so for example, if you want to change what's displayed by default, histogram will, so I can just run this to show you. So by default, histogram will use your variable as the x-axis and count in each bin as the y-axis. So in this case, of course, you always need a y-axis to make a plot, but this is a transformation of this data that Ggplot is doing internally. You can specify other transformations in various ways. But again, I'm not going to get into the details of that today. So this is a simple histogram, right? So a histogram works by taking bins of your data and counting up the number of observations in each bin. You can specify the width of the bin. So in this case, I'm specifying 2. So for every 40 and 41, it counts the number there. You can also specify a number of bins. If you want 50 bins, then it will divide the range of your data into 50 bins and then summarize it that way. There are a number of different ways that you can make this sort of same kind of plot. And to sort of demonstrate the differences between them, let's go back to using a grouping variable. So now we're going to make a new variable in our Gapminder data set called decade, which is just going to be the year divided by 10 and then dropping the decimal. So 1960 to 1969 will be 196, etc. So it's basically just marking decades. And we're going to use that as our grouping variable. So again, here we're going to specify color equals decade. Color by default applies a grouping statement. And we're going to assign this to this aesthetic, right, with the data with decade created, and then a single variable life expectancy grouped by decade to, we'll call this life expectancy distribution LEDist. And then we can look at 3 different ways of displaying that data. So histograms work quite nicely and can be quite informative when you have only a single or a few categories. But if we run this, we'll see that when you want to look at, say, 10 distributions, or what is this, 6 distributions that are mostly overlapping, this can be pretty hard to interpret. It creates a stacked histogram so that you get, these bars here represent the proportion of the counts in this bin that come from each group. And by using color here, we're just outlining the boxes. I'll show you how to change that in a little bit. You can replace this with fill to make histograms maybe look a little bit better. Frequency polygons, which are basically just lines fitted to histograms, look much better here because you can see they don't end up stacked. And even better for sort of seeing the trend and how the change in the distribution has, shifted over time is probably these kernel density plots, which are fitting a smoothing function basically through the data. Right, and so we can see how the peak of life expectancy has shifted to the right through the decades. Note that, again, like the default y-axis varies here, so both histogram and freq poly use count as the default y-axis. A kernel density obviously uses density as the frequency. And again, there's various ways that you can modify these commands. Okay, so let's see. The last thing I'm going to cover, and then I can hang around for questions or to discuss whatever you're interested in, is categorical data. So another kind of very common sort of simple plot we might want to make is a way to sort of summarize these distributions by decade. So like rather than plotting the entire distribution like this, we might want to do something like a box plot that turns this, reverses the orientation of this kind of thing, and then summarizes those distributions in some way. So let's look at a few different options here for how we can do this. And I'll just run the command here, and then I'll go through each of the 3 plots. So our default plot here is just, again, we create the decade, and then we use our x-axis is our categorical variable, right? So here we're going to have our groups on the x-axis, and our y-axis is life expectancy. And then we're just calling, in this first plot, we're just calling the default genome box plot, no additional grouping or anything like that. And what we get here is 1 plot for each decade. This probably even more than the density plot illustrates the way that life expectancy has changed over time. We might want to look at this, say, separately by groups, right? So we can add a grouping statement to the aesthetic, or we can add a grouping statement to the box plot. The grouping statement we're going to use here is actually initially for this middle plot, we're actually going to use the fill statement rather than the color. So fill changes the color of the interior area of a solid thing like this. So like box plots or histograms. And so if we do this, what we'll see is we get the same thing, decade, life expectancy, but now we have a separate box plot within each decade for each continent. Right, so we can see both the trends for each continent over time and how the disparity among continents has changed with decade. The color option does the same thing, except it changes the outline, not the interior of the box plot. And what you can see here is that we can also say reverse the grouping variable and the categorical variable. Right, and so now we're going to put the continent on the x-axis and the decade as the grouping variable. And so now we get, within each continent, we get the trend, you know, from 1960 to 2010. Right, so whichever is the x-axis is going to be the sort of outer variable, and whichever is your color or fill statement, your grouping variable, is going to be the inner variable. Okay, so that's just about 45 minutes. So I think I'm going to wrap up and leave a little bit of time for questions. But I just want to show you one kind of more complicated plot here, which uses a facet grid, which is a command that arrays rows and columns of similar plots. And so what we're doing here is making a plot that has life expectancy on the y-axis, log GDP per capita on the x-axis, and we have a separate plot for each continent and each decade. So this is the sort of thing that is quite straightforward to make in Ggplot. We're just adding one command, this facet grid command, which splits your data by rows and columns and makes a separate graph for each one. But this would be very, very hard to make in something like base R, where there's, you know, not as good ways to kind of control these sorts of similar grid type plots. And of course, you can apply themes to this as well, right? We could say, right? And that has a different look depending on what you're going for, right? Theme minimal might look pretty good for this. Right, so something like that, you know, something you could almost stick into a paper just as is, right? And this doesn't require that much work or customization to get things like this in Ggplot. Okay, so I'm gonna end there. Just simple review, the basic sort of conceptual things that I'm hoping that we got across. A Ggplot is built up from a data set and then aesthetics, which establish a coordinate system, axes, all of those things, and then one or more geomes that map the data to those aesthetics. There's lots of customization options, but for many relatively simple or even more complex plots, relatively little changes from the default options are needed to make things that look good. I've introduced a small handful of possible genomes here, but of course there's many, many more options for all sorts of different kinds of plots. One-dimensional, two-dimensional, you can make heat maps, you can make bar plots, you can make, two-dimensional scatter plots that show points, but like hex bin plots where the color of a grid in a 2D scatter or the two-dimensional scatter plot is proportional to the number of points that are in that grid. Lots of things like that, and this can get very complicated, but I think the hope is to sort of show you how it's easy to do simple things and it's easy to sort of explore and poke around, and that Ggplot itself is actually pretty approachable when you think about it in this sort of system. Okay, so I will stop the recording.